Hello and welcome to the lectures on state space approach to control system analysis and design. In this week, we have considered the application of control design techniques to the design of a nuclear reactor. We considered the periodic output feedback technique. We considered the fast output sampling based technique. Before that, in the preceding lecture, we considered the application of simple output feedback based scheme for design of closed loop control system. And we simulated the responses and we saw that either of the controllers lead to stabilization and one can optimize the design or one can redo the design various in some iterative manners to obtain a good controller for the system based upon any of these three techniques. Of course, one is also free to either design a state feedback based control or any other controller. Now we come to a different example which is in the area of estimation, state estimation. A few weeks back in our lectures we had discussed the Kalmanfiltering technique for state estimation. And this lecture is one example of application in a real situation pertaining to nuclear reactors. And it is intended to bring out some important considerations in selection of the design parameters for the Kalman filter as regards this particular entity or a small system for control. So essentially we are going to attempt the design of Kalman filter and its selection of its parameters so as to get a good design with the intent to improve the response characteristics of a vanadium self-powered neutron detector. The problem will be stated little later. Let us first review, have a look again on the Kalman filtering. Now, it was told in the lectures on Kalman filter that it is an optimal estimator. This is another way of putting how it works. This is one can make it recursive. That is one thing. However, main thing is this, that it first predicts the state of the system and then applies correction to that predicted state to get the corrected state. And this correction is applied so as to minimize the square of the estimation error that we saw. Now, this is tried to show here that based upon the knowledge of states xk hat and this covariance matrix pk, and using the system model we calculate this this is xk minus 1 and pk minus 1. Based upon this knowledge we calculate xk hat minus, please take note of this minus sign, and similarly pk minus. So these are a priori estimates. They have been computed based upon the model of the system. Now at the end of that sampling interval the measurement is available, and so correction k times yk minus that some yk hat or yk tilde will be applied to get the correction, and then we will get the corrected state. Now using this corrected state we will calculate at the next sampling interval and so on. So this is how it operates. The state is predicted using the system model and it is corrected using the deviation of the actual output from the computed output. This gain K, which is called as the Kalman filter gain or simply the Kalman gain, is calculated so as to minimize the square of the estimation error. This we saw in that lecture. We proceed ahead looking at the system model. So generally we studied this system. However, we gave consideration to noise inputs, noise terms W and V. Of course, when it is modeling of systems, two things happen. One is we are not able to take into account the noise. Other thing is a lot of unmodeled dynamics remains due to assumptions, etc. So the mathematical modeling of systems has errors. One is noise terms not considered, other is due to simplifying assumptions, etc., some component of unmodeled dynamics. Of course, this is not considered in the Kalman filters. We are only considering the noise terms, and they are W and V, and they are Gaussian. We saw that. So E WK transpose is some QK Q delta K, and similarly this one E VK transpose is some R. They could be constant or they could be varying over the time. So we have the knowledge of the system matrix, the input matrix, the output matrix, and characterization of the noise terms as regards the Kalman filtering for estimating the states of the system. These are the equations. The notations may be slightly different from the notations which I used in the giving lectures on the Kalman filter. But irrespective of the notations, let us understand that given the system model, I'm sorry, one UK minus 1 is missing here. This is the equation which is same as this equation. However, the system matrix is denoted by phi. There it was F. I'm sorry for the non-uniformity of the notations. The input matrix was denoted by G. Here it is gamma. And noise term is not there in this. So we predict the system state from the knowledge of the previous estimated state and the input. No noise consideration as far as the prediction is concerned. And we also predict the value of the state covariance matrix, which is given by this. QK should be known or should be assumed. Now once this is called as a priori state and a priori value of the covariance matrix. Using that we calculate the Kalman gain. R is either known or to be assumed. This H is the output matrix. This P is here. So we have calculated the Kalman gain. We are ready to apply the correction. So at the next moment, see this is the moment K minus 1. Just before that we have calculated the predicted state. At kth instant we get the measurement, the value of the output. And that minus, this is the computed value of output using this predicted value of the state, you can see. And this is what is called as innovation. So the Kalman gain into this deviation is the correction applied to this predicted state, and thereby we get the corrected estimate. This is closure, this has better properties, this has less uncertainty in the presence of noise, this had larger uncertainty. We have also calculated pk, a posteriori covariance matrix, from the knowledge of a priori pk and Kalman gain, and we have stored this to utilize here. So this is how it goes recursively. Now Q and R in a practical system, one expects for the design of Kalman filter to be available, but generally it is not, and one has to take some way to obtain good values of Q and R. So that is also explained in this. So in this application, Q and R are not known actually. However, based upon several trials, etc., it has been optimum values of Q and R have been found, so that the correction to states is good and we get good estimate of the state. Now, as I said, this is being applied to Vanadiumspnd. We will come to Vanadiumspnd. This is the representation of the same thing through a state diagram. This is the system representation. Again, I beg your pardon, in the equations it was phi and here it is f. The system matrix is denoted by f. F and phi, please treat them identical things. And similarly, I don't find the G here. Directly W is driving this system. It is that G is missing. So we have that F for phi, G and gamma are to be treated as identical quantities, and of course output matrix is denoted by F. So actually G times gamma times UK is supposed to come here. This is UK, this is gamma. And to that the noise is being added. So this is the process system. HK is the measurement model, so we get the output. This is the ideal output. To that we add the noise to get the actual output of the system. And this output is coming. To that we compare that model output. This is the model running, and this is the correction through the Kalman gain. This is the deviation, the innovation into Kalman gain, that gives the correction. This is the predicted state, this is the correction, and so we get the estimate, which is a corrected estimate. Okay, now we come to the problem statement. Actually, in a nuclear reactor, the one, for example, we considered in the case study, we require the measurement of neutron flux in the reactor. And there we considered a sensor called as ion chamber along with its amplifier, which is mounted X core. That means not inside the core, outside the core, somewhere in the reflector near the core boundary. And it gives a signal proportional to the neutron density. When the reactor is large, for example, a pressurized heavy water reactor in India of the capacity of 500 megawatt or 700 megawatt could be something like 7.5 meters in diameter and 6 meters in length. And the conditions at different points in the reactor may be different, and it needs to be monitored and controlled. So we use a lot of in-core detectors. In-core means going inside the core. So they go in the core, they are placed inside the core at several pre-decided locations, and they give distribution information about the distribution of the core neutron flux. Now in control, generally we use self-power neutron detectors which have emitter material platinum or cobalt. I will explain what is emitter material. So the self-power neutron detectors which have platinum or cobalt as the emitter, they are prompt responding detectors. Their response is within much less than milliseconds, and their response is usually characterized only by the response delay of the associated amplifier. Almost instantaneous they are. However, they have very poor accuracy. The vanadium self-power neutron detectors, they are highly accurate. However, they respond slowly to variations in neutron flux. Now, in typical instrumentation, one requires accuracy and good response both. However, here this set of detectors have poor accuracy. This detector has poor response characteristic. So attempts should be made to make the Vanadiumspnd prompt responding in some manner. And one way of doing this is to use Kalman filtering approach. So if it is successfully done, then Vanadiumspnd, along with that its associated Kalman filter, is having accuracy and promptness in response, and so it can be considered in place of cobalt or platinum detectors. Now we see the construction of a self-powered neutron detector. So there is one emitter, there is one insulator which is either manganese oxide or alumina. There is an insulator inside that emitter, and as I told, this emitter could be made of cobalt or platinum or vanadium or rhodium. There may be more materials like silver possible. So there is a thin emitter, cylindrical wire emitter surrounded by insulator, and this is all enclosed in a sheath. The whole thing is about 200 to 300 millimeters in length, and just about less than 5 millimeters in diameter. Very small. This thickness is very small. Now what happens when neutron enters the detector? It gets absorbed into the emitter material, and there are two possible effects. One is the emitter material will immediately, after gaining the neutron energy, release a gamma ray, and then it will stabilize, or it will release gamma ray as well as it will undergo radioactive decay. So cobalt and platinum like detectors, they operate on that first one, that their nucleus will absorb a gamma which is equivalent to photon. It will absorb a neutron and release gamma which is equivalent to photon, and that photon will do photoelectric effect, pair production and Compton effect in the insulator material, and all these three phenomena give rise to electrons. These electrons, if wired, if harnessed properly, gives rise to a current, and so this emitter current is proportional to the number of neutrons which are entering and causing interaction with the cobalt or platinum detector. Based upon that, three phenomena: photoelectric effect, Compton effect and pair production. And this is why it is called self-powered, because it doesn't require any power. These electrons will, because of that, a small voltage difference will happen, and so a current will flow in the circuit. In case of a vanadium or rhodium spnd, this gamma is released But also this compound nucleus, see vanadium 51, the vanadium with a mass number 51, this has absorbed one neutron, this has gone to vanadium nucleus with mass number 52 atom. It is in excited state, it has more energy, so it releases gamma and it comes to ground state, almost the ground state, and then it undergoes beta decay, thereby it releases electron. And so there are two currents. One is this I gamma, the current dependent on this gamma through photoelectric Compton and pair production effects. And this other component I beta, which is dependent on this beta decay of the vanadium 52 nuclei, thereby it converts to stable chromium 52. So you can see this, take a note of this number, 3.77 minutes is the decay half-life, and the corresponding time constant of vanadium Sp1d will be of the order of 5 minutes. That is the problem. So we require a system model for application of Kalman filter. So we first model the vanadium Sp&D, and based upon these phenomena, this production of I gamma and I beta, their sum is the total current. I total is I gamma plus I beta. This total current is actually reflected in the output. So that total current, this one, comes through some intermediate state variable. So I is, this is here, I delta I by sensitivity Fp delta phi. This is one state variable. So delta I by S minus Fp into delta phi is some state variable. Let me denote X. And so delta I is S times X plus Fp into delta phi. So the vanadium Sp&D current delta I is given by this expression, and this X is the state variable. This is the state variable, one of the states in the system. So this is the vanadium Sp&D model. We have the reactor model given by these two equations. Now they should look familiar to you, having attended the case study course, having attended the lectures on case study of nuclear reactor. This is the variation of neutron density with time. Of course here the symbol is phi, there it was eta. And this is the variation of delayed neutron precursors concentration. We have not considered here, to keep the thing simple, the dynamics of the control rod, the dynamics of the linear amplifier. We have just taken the linear amplifier signal as the neutron flux and the delayed neutron precursor concentration as the state variables of the system. In these equations, this reactivity rho, this varies depending upon the control rod position. However, for application of Kalman filter to vanadium Sp&D problem, this reactivity variations has been expressed through a random walk model. So derivative of delta rho with respect to time is treated as 0. And of course we are interested in phi, because the flux, this phi gives rise to the current in Sp&D, and we want the estimate of phi. So once we get phi, then that is the actual flux in the reactor. So we have to put Kalman filter here, and we have to get that estimate of phi, the phi hat. This is the problem, and this is the system model for solving that problem through the application of Kalman filter. So we have one state equation, two state equations, and third we have a fourth order system model for application of Kalman filter to this Vanadiumspnd problem. Now this is how it goes. Reactivity gives rise to the neutron flux variations. It was shown by these equations. This reactivity gives rise to this flux variation. That flux is measured by Vanadiumspnd. Its associated amplifier time constant can be ignored. Vanadiumspnd, its associated time constant can be ignored. Vanadiumspnd itself has a large time constant, which is modeled as a first order system. It is sampled, and this is the measurement of flux using the Vanadiumspnd. This is the measurement signal. Now parallelly we have the Kalman filter running as depicted here. This is the system matrix phi. This is multiplying to the previous estimate. We get the prediction. To that prediction we are adding this k times this difference, and so we get the corrected state, and through an output module we pick up that phi, which is the estimated flux, which is phi hat. So this is how online implementation is done in this application, and I show a few responses that were obtained. First of all, of course, this experiment was done, you might have heard, in a reactor was established by Department of Atomic Energy long back, known by the name Apsara. Now this reactor does not exist. It has been decommissioned, and a new reactor, Apsara U, is operational at Bhabha Atomic Research Center, Tramde. You might be aware. So these experiments were done in Apsara reactor. In Apsara reactor, a Vanadiumspnd was specifically installed, and because it is a research reactor, the neutron flux could be varied in some arbitrary way. So neutron flux was lowered. This is the steady state. With respect to steady state, it was lowered, again raised, again lowered, again raised, and so on. This was done at one rate, then again the same thing was done at different rate, and then again it was re-stabilized to this operating flux. In a research reactor, one could do this kind of experiments. The Vanadiumspnd, you can see, because of the large delay of the order of 5 minutes, the output of the Vanadiumspnd is very smooth, third version of this actual neutron flux variation, because huge delay. If it was prompt, it would have shown the same waveform in its signal. So this is what we want to do. We want to design the Kalman filter so that we get from this one, this one. From this we want to get this through a Kalman filter. So when we implemented those equations and when we selected this, if it is not readable, let me write to you. R was selected as 1. Q is selected 10 to the power minus 6, 1 into 10 to the power minus 6, of course. And if the Kalman filter is algorithm is run offline over this time, of course it is first allowed to run several times before t equal to 0. It is on, so it has achieved some kind of steady state, and as the system is undergoing transient, this recursive implementation is done even in the offline situation. So when it is done for these values of Q and R, this is the estimate. So observe that I show this is the actual variation of the neutron density, And if you see here the estimate, it is still characterized by delays. And this is the difference. This is the innovation. Actually, the axis title is output estimation error. That is not correct. Two things one should see. One is that estimated flux is so very smooth, however it is delayed, and so there is trend in this error. You can see these trends are reflecting there. It is understood that this choice is not a very good choice. So Q is varied, and this result is for the same data set, however for Q equal to 10 to the power minus 3 and R equal to 1. Now the estimation has improved, and also this trend is absent. It is there, but the amount by which it is present is less. So that means one can play with the Q more. So this is the result with Q equal to 0.075. Q was very small, it was increased, and it is even further increased. And the trend is almost absent. So what we see, that as we are selecting a good value of Q, the estimation becomes good. However, it is accompanied with noise. You can see the presence of noise here. Here it was not present. It is very smooth. Here some noise is present. Here even more noise is present. However, the trend completely goes. There is almost, the trend has almost vanished. And that is an indicator that Kalman filter is parameters, this Q and R parameters are optimized. This is for another Q, which is Q equal to 1. Again it is showing that noise has increased, however trend has vanished. Output estimation error is quite random. One can check its whiteness property. Mean will be 0 and variance becomes constant. So that is shown further for Q equal to 100. Q is further increased. Probably it has made more noisy and there is not much improvement as far as the estimation error is concerned. So one does this kind of numerical experiment for several values of Q and R. Only one particular set is shown here in which R is 1 and Q is varied from 10 to the power minus 6 up to 100. And all these, when they are plotted with respect to log Q, so of course Q, I should mention that Q here is a 5 by 5 matrix. There were 5 states, 2 characterizing the reactor, 1 characterizing the Vanadiumspnd, 4 states, 2 characterizing the reactor, 1 characterizing the Vanadiumspnd, and 1 that random walk model for the reactivity. So Q is a 4 by 4 matrix, and it was selected identity into a multiplier mu, and that what we are talking here when we say that Q is 100 or Q is 1, then it is identity. This is 0.075 times identity. R of course is a scalar, so R is not a problem. So that multiplier to identity matrix, log of that on x-axis, and that covariance of this error at various time, if this is plotted, then for small q it is large, and as we go on increasing q through a parabolic trend, it is reducing like this. Means it is going closer to some kind of optimum, or there is probably a knee region or a knee point somewhere, based on which one can select that multiplier to Q. This is covariance of the estimation error. So this is for large Q and this is for small Q. And here we see it is definitely having some kind of a minimum. So based upon this trend, one will probably pick up a good value of Q, which will give optimal estimation of states. So this is how in a practical scenario when Q and R are not known, one collects data and does offline analysis, and from offline analysis, from monitoring the covariance of error, one can optimize Q. And once Q has been optimized with that value of Q and the R which was used in offline analysis, the system can be implemented online for online correction of response of Vanadiumspnd. That is how one goes about it. So that is it. So we have shown the application of Kalman filter for improvement of response characteristic of Vanadiumspnd. What we meant is that we pick up the Vanadiumspnd signal and we compare to the inside the Kalman filter to the computed Vanadiumspnd signal. We correct and thereby we get phi hat. So this is the actual flux in the reactor. This is Vanadiumspnd along with its amplifier. At this point, this current of the Vanadiumspnd is delayed. So for example, if phi changes like this current I, it is characterized by a huge delay. So it will not rise immediately. It will have a delay. And it will rise to that value characterized by this time constant of 300 seconds. Now, if one uses Vanadiumspnd for monitoring the neutron flux, one will not see that flux. One will see this signal. And the operator will feel that the flux is rising slowly. That is not correct. So operator should be shown this one. So from this, through a Kalman filter, if it is done, then what comes out is this or something close to that. And that is the success of application of Kalman filtering, that this is close to the actual variation. One requires to do processing as per the Kalman filter. And as was demonstrated, covariance of either the innovations or the output is a very efficient parameter, a very nice parameter to be looked at to tune the Kalman filter parameters Q and R, which was done. This could be one way. In literature, you may find several ways of tuning Q and R. They are there. Or probably from the measurements, you can extract the values of Q and R and one could implement. This is a way which was adopted in this particular application. So through this application example, I have tried to bring to you a real life scenario how Kalman filter is applied for a state estimation. Thank you very much.